Hello, everyone. Thank you for joining my talk. I'm Lucian, and I'm going to talk to you about designing concurrent C++ applications. You can find the presentation slide at the address shown on the screen, and along with some more materials in there. So, the first day of the conference, Anastasia showed a nice graph with C++ development frustration, and the first place is concurrency, pretty far ahead from the rest of the other frustrations in the C++ community. So I said to myself, well, that's a very great introduction to my talk. And later I realized that adds a lot of pressure as well, because I need to do a good job. Most of the frustration is related to concurrency, so I really need to do a good job. So before getting into the core of my presentation, I have three questions that I would like to propose as a poll. So the first one, what is the first thing that comes into mind when somebody says add threading to your application? Let's wait a couple more seconds. The results are still changing. Okay, so they kind of stabilized. About 36% says performance, 32% says synchronization muted locks, and then safety 30%, other 30%, and 4% bugs. Let's I can also share the result. That's good. Performance is increased a little bit. Let's move on to the second question that I'll have. And that would be, for multi-threaded applications, where is most of your time spent? With respect to threading, forget about the business logic and whatever, just focus on the threading part. Where is that spent? Okay, the results seem to be stabilized. So those are the results. Design seems to be 46% of this, adding synchronization 8%, bug fixing 27%. I was not necessarily expecting this, but that's a very good point. I like this result. And then let's move to our final question, which is, would you use a model in which synchronization is not needed, for threading, of course? Okay, so the results are somehow stable. 83% says yes, and 17% says no. I would be curious to understand the reasons why, but that's part of the talk. What I'm trying to get at. Okay, so rules of engagement. I want to welcome questions at any time. If you do have questions, please feel free to raise your hand, and our track host will allow to unmute yourself. And if you prefer to speak, please do that. Or if not, just type it in the Q&A. I'll try to watch the chat window as well, but I'm not sure if I can follow that. I'm going to show a lot of examples. Please try to focus on the concurrency parts of the examples, not the rest of the boilerplate, just to make that are there just to make the examples running. Okay, the promise of the talk. What I'll try to do here is to build on and build some high-level concurrency abstractions without any locks, with some exceptions that I need to prove some points, that are with high performance. And most of my talk is going to be based on showing you a lot of examples. So I'm planning to show you 30 examples with concurrency, none of which uses at the core locks. We just using some locks in the performance discussion for that. So that's what you can expect from the talk. This is the agenda for the talk. I'll start with some more high-level section and then just go over a lot of code examples. So threads considered harmful. This is the title of a talk that I previously done for ACCU this year. I'm somehow assuming that you're familiar with that talk. Trying to go through some of the concepts in this presentation, but just a very high level. If you're watching this online, please try to see this talk on YouTube before this video. So pause here, go back to this other one. What's the main thing? When I say threads, I mean raw threads plus synchronization. Of course, in concurrency, what we generally mean by multi-threading, we need to use threads. But when I say threads considered harmful, I mean raw threads and synchronization, which mainly I mean locks. And the reason why I said that is that there are a lot of performance, a lot of problems with threads, performance, understandability, thread safety, composability. And the main reason is you're likely to get them wrong. So you probably, by the results that Anastasia showed, you've probably been through the pain of all these things. And the talk just tries to do it at the high level without too many code examples, tries to come up with a general method of solving concurrency problems that doesn't use lock, avoid safety issues. And here, a critical point in here, you do have to follow some rules. You can't just get safety by free. You have to follow a set of rules, but those are minimal. You'll have good performance, and something that people may not often think about, and for me is very important. This method is composable and decomposable. You can get a big problem, you decompose it in smaller pieces, solve the concurrency in there, and then you recompose this thing. And the method is based on using tasks, or people call them raw tasks, but whatever, just let's call them tasks. And I mean by a task, an independent unit of work. Independent means that all the dependencies of that task are explicit, or you can say depends only on the inputs. Has some constraints and some preconditioned tasks that need to be run. That's everything that need to be taken care in terms of safety. And then by unit of work, I mean, for the purpose of the problem, it doesn't make sense to divide it even further, right? You can have big tasks and you have small tasks like one instruction. Most of the cases, you probably don't need tasks of one instruction. So we're just going to collectively talk about them as units of works of tasks. And the main thing that I argue in that talk is that any problem can be represented as a graph of tasks like this, in which you clearly set up the dependencies So those arrows that I'm using in here, and I also have something in here with red constraints. Not necessarily one task needs to run in front of the other, but they cannot run in parallel. That's the idea. So this is very similar to flow diagrams. It's doable for every type of problem, and if you can do that, then you don't have to use raw threads, you don't have to use locks, and most of your safety problems disappear, right? I mean, if you're strictly doing this, then all your safety problems will disappear, threading safety problems. I did wrote some articles in Overload for that, and basically I call them theoretical results, or concurrent algorithms can be expressed by such things. Safety is ensured, you don't need to do any locking for that. You basically have your dependencies for that. You have a high efficiency if you're using a greedy algorithms, you have high speed up, and actually computed somehow theoretical minimum speed up that you would have for certain problems. And it's easy for you to have a composition and decomposition for those things. Okay, in this talk, what I'm going to focus is kind of the same concepts, but I'm trying to translate them into code. I'm going to walk you through 30 examples, 30 code examples. You can find them on GitHub, and just trying to walk you how you can design complex, different types of concurrency problems. So complex applications with different types of concurrency constructs in them. Initially, I had 31 examples, but at the last minute, I realized that one of the examples was not complete. So sorry about that. I'm going to just skip that example. What I'm not including in this talk is GPU, CMD, and coroutines. So coroutines should not be associated with threading. They are simply two different things, right? Just like you don't associate lambdas with threading. Those are separate concepts. Okay, so let's try to dive into the code examples. An introduction to concurrency without using locks. Okay, so first we need to have a hello world example. What I'm going to do right now is I'm going to just switch between my presentation and my code. So this is the hello world example that you would need for this thing. It's a simple main function that just has some concurrency construct in it, and inside that we just print hello concurrent world. For all my examples, I'm going to use a library that I built called Concur. You can also find it on GitHub. For the purpose of the talk, the library doesn't matter. I mean, I'm going to use just this library, but my main point is I want you to walk out of this talk considering that any library that has certain features can also work with these examples. And in this particular example, the interesting construct here is spawn and wait, which basically tells the library, hey, I have a task. You see, I have a lambda over here, and you can execute that concurrently if you like. If you don't, just execute the serially. That's up to you. This is how, it's another interesting point. I will talk more about concurrency. So I'm telling the library and the application what's allowed, and I'm not necessarily talking about parallelism, what's actually being executed in parallel. Right, so I'm moving the discussion at the design point, and that's pretty nice because of the poll results that you mentioned design in there. I'm trying to make this thing a design problem and not necessarily an implementation or bug fixing problem. It's a design thing. So this is how you would write a simple hello concurrent world program. The second one, which probably is the most interesting, the thing that you would want to do when you have a concurrency application, is you want to create concurrent work, right? So you have something like one task or one block of execution, and then you want to somehow get to two blocks of execution. For each of these things that I'm walking through, I'm just going to put simple diagrams in here. I find it very easy to express this by diagrams. That tends to be more like a design thing. So, and you can simply visualize your problem as a design space problem, not necessarily an implementation. How do I put more threads and more locks in there? And the example for that is this. I'm going to focus on this part over here, and then I'll just walk through the other thing. In here, I have multiple tasks that I want to run concurrently, which basically prints the message, how did the multi-threaded chicken cross the road? And those tasks are represented by these lambdas, which just call a simple function that just prints a message. I apologize, I'm using printf. If I offended somebody, I do want to apologize. And basically, we are telling the library this thing can safely be run in parallel. And I'm going to run this example, and you can see several invocations of this. And you see that each time I run it, something changes. How cross did chicken the multi-threaded the road? Or how did multi-threaded chicken cross question mark road the? And I'm using a little bit more machinery in this example, just for the sake of demonstration. They're not necessarily related to what I'm trying to show here. I'm trying to create a task group, which is something like here you can put multiple tasks and you can execute some operation on that group of tasks. One of the operations that you can execute is you can wait on those things. And the way it's done, this is a busy wait. So it doesn't block you on some semaphore or lock or whatever. It tries to take some tasks that are in the system and try to run them so that the thread that's doing the wait is also contributing to making the work finish faster. And I'll get into some more details about that later. And then you can see all my tasks. I just put it a group in here for all that. And the other thing, which you'll see in my examples, is I put a profiling helper thing, which just does some sleep at the beginning of the end, and depending on some compilation flag and some macros that just instrument my code to see what's happening. And with that, I'm going to switch to an interlude. I'm going to show you a little bit of a Tracy Profiler. I'm frequently using this to diagnose performance problems, and it's very useful for threading. And I'm showing you how you can spawn. With that, I'm going to show you a little bit about spawning tasks and waiting for them, task system, and all that. So with that, I'm just going to say enable this. And I'm going to rebuild this thing and not run it, sorry. I'm just going to run it with Tracy. And this is how Tracy works running my program. It's somehow like a timeline visualizer. You see here the threads. One is main thread, the other are worker threads. And with the annotation that I was making, you would see one block for each annotation that's in there. So I have one annotation for main. So this thing will annotate the function main, and it will actually annotate everything from line 16 up until in here before the destruction of this object. And then in the print message task, I also have this with some message. So if I hope you can see this. If I just hover around this, you can see with yellow the text that this is printing. And so you can see that all these tasks are running parallel, and you can see that if you zoom in, they'll start slightly different times, and of course they are waiting at different times. And you see that the main thread, which is this one, will actually take a little bit longer to run compared to the last time. So that wait thing, we just wait for everything to finish, and then you say, yeah, I have nothing to do, does some more checks, and then exit. That's 34 microseconds on my machine. So that's a pretty decent performance we have in there. I'm not going to insist too much on performance, but that's it. Okay. The other thing that I should have mentioned, task systems. So what I'm doing in the library, I'm having a task system that that creates a number of worker threads equal to the number of cores that it can see my machine has. In my case, 12. Actually, I'm having 6 plus hyperthreading, so that is 12. And then it will try to fill up those worker threads with tasks that I introduce. I'm not going to focus too much on how the task system works, but that's the general idea. Are there any questions so far about how the setup? I'm not going to repeat those things, and we will keep building on those smaller things. Okay. Okay, Philip asked me, how are you going to implement the task system without using mutexes and atomics? I didn't. The whole point is I'm not promising you that there are no mutexes or atomics in here. What I can promise is that you can build your applications without worrying about mutexes and atomics. And please forgive me, sometimes I use atomics, so that's just my bad habit. Hope that it doesn't bother you that much. I'm really against mutexes. Mutexes should not block. You should not block your threads. That's something that I try to make into the other talk, threads considered harmful. That actually spans from go to consider harmful. It's not like you don't have gotos in your code. Actually, probably the most frequent operation that you have on your processor is some form of jump, right? Which is a goto, but that's hidden from you. That's hidden by the compiler. You have a lot of gotos in there, but you're not programming in gotos. And I want the same thing with threads. Hope that makes sense. Okay. Delay continuation. I'm going to show you 3 examples of this one because you can view it in multiple things. So you can see this pretty frequently for something like SMS, right? You want to text somebody and you're not blocking that person while you're sending that. You're sending it a message and you wait for it to respond. And that's similar, if you transpose this into tasks, it's similar to invoke it and then pass it a callback. That callback is your phone ringing back to you that it received your message. So that callback just prints calling back. And in my case, I just have a struct person that has an SMS, and that at some point after in this case, Alice is been busy with something else. At some point, she would be unblocked and then spawn a task that will say, hey, I'm ready to respond to you. And then it sends the response back by just spawning a callback. So what I'm doing here, I'm creating a task for my caller, right? So it's essentially a callback. Let me quickly run this. I'm going to run it like this. So Alice is being texted by Bob, hey, I'm free, and she's continuing to work. And I do have something that just prints a lot of dots. And at some point, Alice is now ready to respond to Bob, and she calls back, right? So all this happens in parallel while this thing does something else. Let's run this with Tracy. And yeah, of course, I need to recompile. By the way, this is a nice point. So sometimes Tracy still crashes. I'm using a slightly older version of it, so hope that doesn't happen too often here. So that's main. Bob is sending an SMS to Alice. Alice is doing some work. Bob is doing something else in the meantime. And then after Alice is done, she will call the callback. And in this particular case, the callback is called on the same thread. That's the library tries to optimize that and says, hey, I have all the resources available. You can just execute it in here. Hopefully that makes sense. Another form of continuation, you've probably seen this in many applications. Something like I want to make an HTTP request and I don't want to block on that HTTP request, and you're doing it asynchronously. That means you're registering a callback. Sorry, you're passing this thing where you're creating a task, you're passing a callback to it, and then you're doing something else while this thing comes back. I have another example in here just to show that different thing can come at different places. If we run this, you see that if you're making a request to Google with query mutex, it says not found, and if you're querying concurrency, everything is okay. There's a better way to do concurrency. And if we run this with Tracy, let me forget to recompile. And yeah, I just caught the crash that I was talking about. You can see that there are multiple things running in parallel. Probably not going to show you that much Tracy for the next examples. Just wanted to give you the feel that, hey, things are running in parallel, right? We have tasks and we can communicate between actors with these tasks, right? And please note, we're not doing any type of synchronization in here. There is this spawn and wait thing, which I said I'm going to go into a little bit later. We briefly touched on it at the beginning. But we're not doing any synchronization with mutexes. We're not blocking any threads. We're just creating dependencies and working with tasks. Another example is an implementation, very basic implementation of async. So you start an async chain with a value 3, then you'll pass it to a function that just squares it, then you pass it to a function that multiplies that number by pi and returns a double, and then you print that message. And because I didn't want to do template specialization, I just made this return bool. And you can see those functions are pretty clear. So squares the number, this multiplies by pi, and this just prints the thing. And I'm just sleeping so that you can see that there are multiple things in here. And I can start a chain, and then I can do something else in between. In my case, I just time it properly so that this something else takes a little bit more than that. It's not the proper way to do it, but you can see that I'm printing some value while I'm running something else. It's always awkward to do small examples in which you have to block everything at the end. That defeats the purpose of what I'm trying to show. I'm trying to show how to create and how to play around with concurrency, not necessarily how to put everything back together at the end. There will be examples of that as well in following. And if you look at the code, is not that complicated. I'm not going to go through it. It's just like there is a little bit of templates, not very complicated, and in the end, it just works nice. There are some tasks in here, like these ones. Those are tasks, and we spawn them at various places. Whatever. That's now that you know how to fork and create work, you can play around with this. Okay, so I'm giving you 3 examples of that delayed continuation thing. So things like you start a process and then you expect some point to be doing something else. So you have a continuation to what you started, and that everything happens concurrently with what you have. Okay, let's talk about join to just give it off the table. That's the thing in which you have 2 tasks and you need to. There's a question before I move on. How would you say this compares with something like TaskFlow library? I'm always ashamed by these questions because I briefly looked at multiple concurrent libraries, and I always forget first the specifics of those libraries, and second, there are a couple of libraries. TaskFlow is one of them. HPX is unfortunately another one of them, in which I forget to get into details. So please excuse me if I'm not giving you a very clear answer on this one. If TaskFlow can represent tasks, then yes, you can build those type of things with TaskFlow. Actually, to be honest, it's not extremely hard to implement a task-based concurrency library yourself. So I would say that this thing is pretty generic. You don't have to bind it to one library or another. Okay, join. So in here I have 2 examples, example 1 and 2. And what I'm doing is I'm having a finish wait abstraction that I can call wait at the end. And then I can spawn multiple tasks. And when I create the tasks, I can tell them what to do after they're done. And in this case, I take the already made continuation from done and just say, you can just tell finish done that you're done. And so all these tasks, what they will do, they will execute do work 1, do work 2, and do work 3. This thing says I don't need a group for them. And then it will just call this functor that finish wait will expose. And in the end, I'm going to do a done wait for this. This is very similar to things that we've done manually with groups, but this is a little bit more structured way of doing this. And in the example 2, I'm having roughly the same thing, but instead of finish wait, I'm going to have a done task. So this is an abstraction called finish task, and this does something. So it does some work, and it does it on this group, and then I can just wait on this group, right? So basically, this example has 2 types of joining multiple tasks and executing one task at the end, and then whenever this task is executed, just let the main thread continue. And I'm just running this, so you'll see something that you have 3 messages in random order. And for the second example, you have those 3 things in random order, and then there is a final message at the end, which is printed by this done work function. So the last task that's in there. Does Concur have a scheduler or already relies on the OS for scheduling? Yes, it does a scheduler. There will be a point later on in the performance section in which I argued that letting the OS handle those things for you. So essentially creating a thread for each task that you have is not going to be a very good option. I'm not going to fully cover that. There is also some, I tried to do some more interactive examples. The ACCU talk, threads considered harmful, to kind of show this intuitively. Hopefully those will be some examples that will stick, why you can't have more threads than the actual number of cores if you want very high performance for your application. So yeah. I'm not going to go into that OS scheduling analysis too much in this talk, however. So the short answer is OS scheduler is not always great at figuring out what to do because it doesn't know that much. At the library level, you know more what you can do. There's another question from Yanis. What's the purpose of blocking the execution with done wait without having something specific to do with it? If you have, why just not attach a continuation? That's the hard part of the example. So all my examples need to finish somehow. So ideally, you would not want to do those waits in here, at least this weight and this weight. This is okay. You can run this in your application, but these ones are not quite okay. You're somehow forcing one of your thread to get off the track of doing proper task-based parallelism and just waiting for something to be executed. That's one thing. And the second thing, you might have latency problems for certain applications if you rely on this more. But I'll just cover that a little bit more in details in a minute, and then at the performance section, I'll be covering that as well. Okay. So that's done. I probably need to hurry up a little bit. ForkJoin. So all the ways that you've seen in here are actually ForkJoin. This is a pattern that has been heavily popularized by people at Intel. And the idea is you would have some tasks that run in one thread. You spawn some other tasks, and then the caller task you would join on those tasks. So you would wait in there, and that's exactly what all these waits are doing. And for this showing this example, I tried to do a concurrent apply, which is basically I'm iterating in this case from 0 to 20 with a step of 1, and then just doing some work. The work is a function that just takes an integer. So you can see this as a concurrent implementation, very naive concurrent implementation of a parallel for iteration. The way I'm doing that is, sorry, this one is the granularity, is not the step. Sorry, I misspoke. So the simple case is if you're less than the granularity, you want to execute this concurrently. Otherwise, you would just, basically I'm trying to implement the divide and conquer method. So you divide this into parts, and then you spawn the two things separately, and then you wait for the result of this, right? And typically what happens is you need another worker to handle this, and maybe the second one is handled by the same thread. But the point is that this thread will wait for both results to end in here. In this case, you don't necessarily have to wait, but assuming that those things will actually produce a result, then probably you want to wait for that result. And if I run this, you can see that it actually does this in parallel. I have two invocations of that with different with different methods. I was just showing you the second one. The first one is very simple, in which I just use spawn and wait. So the two methods, spawn and wait, or spawn with a group and then wait for group, are exactly the same thing. Actually, they're implemented one in terms of the other. So hopefully that makes sense. Again, I'm arguing that spawn and wait, or this type of wait, is okay. You can still build nice concurrent application with that, but it's probably not the best tool you have in your toolbox. So try not to reach it that often. Bad things will not happen too often if you do. So, okay, now that we basically implemented concurrent for, it's actually a good thing that every concurrent library should have. So let's just show one example of that. It's basically the same example. I'm just using the function provided by my library and just print something out. And for the sake of demonstration, let me also try to compile it and run it with Tracy. And you'll see that I have work on all my workers, and some workers, worker thread will take more than one task, and the main thing will just end after the last thing has finished. Now that we are here, one of the things that it's bad to abuse this thing is you're somehow creating small latencies in here, right? So for the purpose of this problem, for 15 milliseconds, the main task had nothing to do. So it had to wait. Under the hood, it's obviously semaphore in there, but that's not necessarily ideal. Again, in a lot of problems, this is, in a lot of domains, this is not necessarily an issue, so you can get by using it. The next one is concurrent reduce. The concurrent for just takes one element and just applies the task to each one. Concurrent reduce. One more thing about this other one, we do have one thing in the C++ standard, it's called std for each. So depending on your library, I don't have such a library that works in my environment, although it's been some time since this is standardized. Depending on your library, you may just find it to work with standard library. Concurrent reduce is, again, some algorithms that is typically seen in practice. There are multiple forms of reduce. I'm just going to say this one reduce, which takes a collection of elements and reduce them to one single value and applies tasks in more or less parallel version to achieve to this result. So I can't have all the tasks in parallel. I do have dependencies between those tasks over here. So if we switch to the code, I'm just trying to create a simple histogram for text, trying to use an interesting problem. I have two texts here. One from Tolstoy, one from The Fall of the House of Usher. And I'm just trying to compute the histogram for those things. And basically the histogram will just try to compute histogram of various things and then just combine them and get a single number for me. And you'll get the histogram for each letter, something like this. And although the original language is different, tends to be roughly the same, which I find very interesting. Okay, the other type of algorithm that's frequently used, it's what's called a concurrent scan. And I'm only going to focus on these three types of algorithms because those are kind of the more relevant one. And the other algorithms that you can build are some sort of variants of these three. The one thing in here is that this is a prefix sum. So think of it as the first thing depends on the first output depends on the first input. The second output depends on the first and the second the input, the third output depends on the previous three things. So essentially, the last one depends on all the iterations. So it's hard to parallelize this. It can be parallelized. The only problem with this is that it adds more work compared to the serial version of the algorithm. So that is how the diagram looks like. It's not important necessarily to know the detail, and I'm just trying to do this thing in which I'm trying to create some consecutive sequences, and then I'm just trying to calculate the prefix sum for them, and I'm having an operation that is just called to do that thing, and it just does. I'm not going to explain too much. It just does what essentially is here on this slide. And again, for this, I haven't listed in here, but we do have standard library algorithm for it. Now let's switch gears. So the first one, up until the spawning and the waiting part, up until concurrent 4, everything was a kind of a base concurrency pattern. So those are all the things that you need to know to actually build complex concurrent application. And since then, we're trying to refine them. So we looked at three major algorithms to see how they work, and now we're going to shift direction to some other forms of structured concurrency. Another one is task graphs. You may have problems in which you can easily represent them as static graphs. So those are things that you know at compile time, what would be the dependencies between those tasks, and then you can simply say, now start this task and execute it. I'm just trying to give one example here, which is something that processes some HTTP server that processes events. And it reads the request, it passes the body, authenticate, log start the event, allocate resources, compute the results, log the end of the event, update statistics, and send back the response. Right? So I have all these tasks. At the end, I'm just going to use a finish task just because that's a good way of using it. And then I just say, hey, I have some dependencies. T1 depends on T2 and T3, T2 depends on T4, T3 depends on T4 and T5. And in this case, T7, T8, T9 just depends on T-done, right? And this T-done is the last thing that I'm executing. And if I'm running this, I'm running this with Tracy, because it doesn't print anything, you'll see that it will run some of these things in parallel, as I said. So you can authenticate and pass the body at the same time. And so in here, you can do three things in parallel. So it tries to use the maximum amount of parallelism that it can use depending on how you express the problem and what resources are available at that time on the machine, right? So always think about this this aspect of the design. Okay, so hopefully that makes sense. Next one is the pipeline. And you probably all heard about pipelines in general. You can also do pipelines, and it appears to be pretty useful in concurrency as well. You have some certain stages that you need to do linearly, and then you can apply that to multiple independent streams. So you can create graphs like this, and those are dynamic graphs, right? So I can have multiple of those stages in parallel, and one thing that it's may not appear to be obvious, you can have stages in which you don't necessarily have to have dependency between these things. So this thing can run in any order. Theoretically, you can have things like you have to have them sequentially run. So like this one, you need to run this one, and then the second task and the third task and the fourth task. You can have them sequentially, but not necessarily in order. So run the second one, and then the first one. That's another way of doing this. And you can run them completely concurrently, in which you don't care either they run in order or whether they run serially. And I do have an example for this. This tries to apply to some video processing. You need to parse a frame, you need to pre-process a frame, you need to decode the frame, you need to post-process the frame, and you need to write the frame to some output and whatever. And in between, I just put different ordering constraints to tell my abstraction what's doing. So this one needs to be in order, and then this concurrent. This one can need to be, so there shouldn't be two tasks of type pre-process frame in parallel, but they can be out of order. And at the end, we probably need to write them in order. And this pipeline has a frame data as an input, and you can give it a concurrency and a task group or whatever. And then you say, push a lot of frame data into it. And for the implementation, you need to have your stages that take one way or another, with reference or without reference, your frame data, and do some processes on that. And then all of these functions will be called in order for each frame. And then depending on how the pipeline is built, different frames can have those things in parallel or not. So you can find concurrency to build out of that thing. Okay, are there any questions so far? Okay, if not, let me go to the serializer, which I think is one of the things that I like a lot, not necessarily because you should use them anywhere, but because it's an easy transition from what you do right now with mutexes to a task-based system. So essentially, serializers are a way to have constraints in your application and say you cannot run two of these things in parallel, similar to what a mutex does. There is a question, executors are one of the top priorities for C++23. Do you think code written with Concord today will need a major rewrite to be C++23 style? I'm going to get to those examples in the near future. I'm not going to cover too much about that. The short answer is most of these examples can be built on top of C++23 executors, but of course the abstractions are not there. So hopefully you'll see more in detail. Okay, sorry, serializers. So the first serializer, I'm having a class that's just doing an average of a running window. So you just add values to it, and then from time to time you get the average for that thing. And the way I've written this code, you cannot call add twice on this class because it will crash. And actually I have some code to prove that it will crash. I'm not going to go over that. And the code looks something like you would have a task that would just add value in there, and if two of those tasks will actually happen to be executed in parallel, then your program will crash. In order to solve that problem, so let's assume you cannot fix this. You have a hard constraint. Some of things cannot be parallelized, so you can't add more concurrency to this class. what you can do is you can push it through a serializer. I'm declaring a serializer object in here. I have two processes, one that just pushes tasks, one that consumes tasks. And in both cases, what I do, instead of just spawning the tasks through my task system, I'll just push them through the serializer. So think about a serializer as yet another, it's actually an executor now that we touched that thing. So serializer is an executor. So you can push things into serializer and just expect that two things will never run in parallel. And if you do that for both the one that's producing the value, the producer and the consumer, then you won't have any problem. And let me quickly show you this with Tracy. So you see here that I only have one add. Let me try to show it this way. Hopefully you can see it better. The colored thing, just where do I have my ads? And you see I have multiple iterations of the producer and one iteration of the consumer. All these add tasks will not be run concurrently, but they can switch thread. That's something that the library decides where it wants to go. Hope that that makes a lot of sense. I'll try to answer the next question. In the meantime, if you have any questions on the serializer, please ask them. In my opinion, serializer is a very important concept to just bridge this gap between mutexes, because this is something that you typically do with mutexes, with tasks. You can build concurrent applications without using mutexes. So question from Sergius, hopefully I'm pronouncing this right, sorry if not. Does Concur library use thread pool task schedule for execution to create thread pools before, or with each spawn it creates a new thread? It executes, it uses a thread pool. The first time you actually do something with Concur, it tries to initialize a thread pool. It tries to get the number of cores that you have from your system and try to use that as the number of worker threads that you have on your system. Creating a new thread for each task is going to be a performance killer, so don't do that. Another question from Yanis: does it make sense for the serializers to support asynchrony? I'm not sure what you mean by that. The serializer is asynchronous, so you can, as I'm showing it here, you can use multiple producer and consumer to push tasks to the serializer. And those tasks will actually be executed afterwards. So in here, you see that my producers and my consumer finish at this point, but the serializer hasn't caught up with all the work, so it's still processing things in here. So yes, it is asynchronous, and it will process all the tasks as soon as possible. Hope that answers your question. Okay, I do have two more examples with serializers. So if you think about the simple serializer as a replacement for a mutex, you can have a read-write serializer. I'm just going to hide this because I was just trying to compare those two things. You can have a read-write serializer like this one here to replace the read-write mutex. So you can have operations that you say they're read, and you can have operations that you say they are write. Any write operation cannot be run concurrently with any reader or other writer operation, but the reads can run concurrently. And you can use that to gain some speed, right? And in this example, I assume that you cannot call add in parallel, but you can call get average in parallel because those are just reading operations. So if you're not modifying your data, then it's safe to call get average multiple times. And very quickly show a run. For this example, I just switch a little bit the constant so that I get different performance characteristics, but it's exactly the same type of problem. This is what happens with a simple serializer. So it takes me 128 seconds to execute this. And with a read-write serializer, it takes me 851 milliseconds. And you can see here that there are a lot of tasks, get average, that are executed concurrently. But whenever you see, where is the other one? This is the small one, no? I can't find the other task. Yeah, whenever you see an ad, you can't see multiple of those in parallel, right? So you have a bunch of ads here, a bunch of ads here, but you can't put ads in parallel with other ads or without with the reader operations. So that replaces a read-write mutex, and there's another example of a serializer, which I call an N serializer, like this. And this one tries to replace what you would do with a typical semaphore. It's essentially a serializer, but you tell it, hey, it's okay if you run multiple of these things in parallel, but not more than a given number. So in my case, 3. This particular example, I'm assuming that I have a backup engine, which is slow, and then I'll just say, okay, to solve that problem, I'm creating multiple backup engines in parallel. I'm just going to put them into a concurrent list, and then whenever I'm triggering a backup, what I do, I'll acquire a free backup engine from the lock-free list. I do the save, which can be a lengthy operation for this, and then when I'm done with it, I'll just push it back. I'm assuming no exceptions, otherwise my example would be more complicated. And again, I'm just pushing tasks into it, and it will just work, right? So I have 3 serializers, 3 concurrent abstractions that can be used to replace the mutexes, the read-write mutexes, and the semaphores. If you think of other blocking type of primitives that we have in C++ standard, you can all implement them with tasks in a similar manner, right? So the only thing is you need to clearly see what are the constraints that you need to execute. And then if you lay out the constraints, the implementation is not extremely complicated. It is a little bit, a couple of hundred lines of code, but it's not extremely complicated to implement that. And that concludes my introductory thing on concurrency. The point that I wanted to make here is that you can use high-level concurrency abstractions, and you don't need to use low-level primitives anymore, right? And if there is one thing that you get out of this talk is that you can use high-level concurrency, which are composable, which are decomposable, and you don't need to have performance problems and safety problems if you properly design the constraints between those things. Okay, let's quickly show some examples of C++23 executors. I'm not going to insist on them. There are 3 things: executors, senders, the receiver, and sender algorithms. Quickly go over that. So everything that I've shown you in here in Concur, they're just executors, and they comply with the C++23 or the proposed C++23 idea of executor concept, right? So the spawn executor, global executor, and a bunch of other serializer and serializer. The reader part, read-write serializer, by the way, it's a little bit more complex. It's not an executor per se. It has two executors. It has a reader executor and a writer executor. But you get the idea, right? They're all serializer. and they can be running parallelly. They have different performance characteristics. So a static thread pool, which is also something that C++23 proposes. In my case, I just created with 3. It has a max parallelism of 3. Global executor, spawn executor have 12 because of my machine has 12 cores. Serializer has 1, and serializer of 3 has 3 max observed parallels, right? So the point is, those are executors, and if there's, in my opinion, if there's one single thing that's extremely important for the C++ community in those papers, is this concept of executors. You can build a lot of nice concurrency abstraction based on that, and not necessarily thread level concurrency. You can go in other directions as well. You have a question with writing code with serializer doesn't look very different than writing mutex code. What's the main benefit of high level? I will get to that in the performance part of it, if time allows. First, that thing with serializer is composable. I'm expressing my concurrency up front. I know exactly the relations between my tasks, and I can reason about that from the design phase. With mutexes, is not necessarily like that. Typically, you can't reason about mutexes. Some people will say they do, but it's a little bit harder. And then there is a bigger gain in terms of performance. Serializer have way bigger performance benefits than mutexes. Mutexes basically block your thread, right? There's nothing you can do while your thread is being blocked by mutex. And believe me, I've seen situations in which real-time system would have a mutex wait and another mutex wait and another mutex. It was a chain of 12 mutexes, and something that's supposed to be under 1 second executed in something like 2 minutes. So that's pretty harsh, right? That's what you can get with mutexes. They're pretty bad in terms of performance. How does Concur compare to HPX? That's the question. I would say they're similar, but my understanding of HPX is pretty limited. I did had a nice conversation previous days with Yanis and sorry, I forgot your name. The other person for HPX. You can do the same things. Again, although I'm planning to develop Concurrent and try to bring it to more maturity and more mature user base, I'm not advocating for a specific library. I'm advocating that those concepts should be our main tools when writing concurrent applications. Nikonj, that's the other name. Thank you very much. Okay, let me quickly jump into the other things because I'm running a little bit late of time. So senders and receivers part of the standard. This is a little bit more complicated to express than executors, but the key idea is that you see the concurrency as a computation pair between sender and receiver. Sender sends some values, receiver typically receive. It's confusing a little bit who's doing the computation, sender or the receiver. But if you get after a certain threshold, then you can work pretty nicely with it. I have a very simple example. This is a receiver that it has a set value, so this can be called by the senders, or can be by calling set done, can be canceled by the senders, or if there's an error, it can respond to error. There's a static thread pool, and then you can connect that to you can get the scheduler out of a thread pool, which you can schedule to get the sender, and you can connect the sender to the receiver. You get an operation state, and then you can start the operation state. So it's a little bit more verbose, but essentially the operation state is a little bit more like a task. So you can think of it like that. And there's another way in which you can do the same thing with submit. You can skip those two operations. The main point here is I guess you can do it in different ways with slightly different advantages and disadvantages. You can prove that those two methods are perfectly equivalent. Okay. I did have another example on algorithm wrappers. Unfortunately, I somehow forgot to finish it, so I'm going to just quickly skip over it. I'm trying to show an example here of creating or extending this feature. So with executors, it's pretty easy to extend. And actually, I had an example here which I very easily glanced over. This is an executor. That's how easy it is to write an executor. It's not much thing that goes into it, and you can extend it to do whatever you like. With senders and receivers, I would say it's a little bit painful to do that, but it's doable. You have to create those things, and the thing that I'm always bitten by is you always mess up some R-value reference or forwarding reference, and then you'll get tons of errors, and then you spend a lot of time trying to debug them. But essentially, you can do that. What I have in my example here, I'm just trying to get a sender that receive a void input, and then I'm going to put it into transform it into a sender that sends the value 3 in there. So this is a sender of void, and then this is a sender of 3, and then it will just go to the receiver. Okay. Question from Jason. Are there any special consideration for using high-level concurrency when writing cross-platform code? Essentially, no. So if your library is good enough, it should work on all the platforms. You may try to work a little bit with performance. You may try different things, and based on your platform, you may try different ways of organizing your constraints and your tasks, but essentially no. Okay, sender algorithms. I'm not going to show you too much on that. The point is the standard, there's another paper, 1897. Hopefully the C++23 standards will have a bunch of sender allocator, sender algorithms that you can use out of the box. There are not that many, but you can build, you can start building more like task graphs out of with these types of sender algorithms, and then it's up to you. And yeah, that may be a little bit more involved. Okay, going back to the slide, let me check on time. So, whoa, that's I'm a little bit late. I'm going to go a little bit on performance topics, and then probably not going to insist too much on those. If you have any questions, just let me know, and then very quickly go over new abstractions and then the conclusions. Okay, so when I say a performance, I mainly refer to throughput. For some application, that also means good latency, but not for all of them. And when high latency is your main concern, that application may be a little bit more specific. So general algorithms do not apply to that. So that's why I'm trying not to focus too much on latency. As I already mentioned, to make this work in a performant way, you probably need to have a global pool of worker, which is configured to match the number of threads that you have on your system. But you can adjust that thing. So if you know you have tasks that do some more waiting in them, that's a big no-no to have blocks and waits in tasks. But if you do have something like that, more I/O, more something that you're not necessarily utilizing your CPU, then you may play around a little bit with that. Or if you have other pools of threads that they need to run, which have dedicated thread, then you can also play around with that. But those were kind of small things. The key insight is if you want to have good throughput, you need to have enough tasks to run concurrently. If you have, like in my case, 12 worker threads, and you always have tasks for them, then your throughput is maximum, right? That's the key thing. That's how you can get performance. You always run something in there. If you're utilizing all your cores to 100%, then you get the maximum performance out of that. In general, you don't have to target exactly that number. You typically want to put a little bit more tasks in there. So it's okay to put 100, even 1,000 tasks in the system, as long as you don't fully utilize your memory or whatever other resources you have, right? So keep your threads busy. I'm going to show you there's a small library overhead, at least in Concur, which I tested, but other libraries have small overhead as well. And if the library has small overhead, of course, you have to do something with the task management. So if the library has a small overhead, the tasks are somehow big enough compared to this small overhead, then you will obtain a good speed up, right? So you can plug this into Amdahl's law and you can have an idea of how big your speed up is. Better, you can plug this in Little's law and you have a minimum bound of your speed up. That's even better. And I'm going to briefly talk about why serializers are okay if you have enough tasks in your system. Okay, code, please. So CPU intensive tasks. No, I don't want to run this. Unfortunately, I did. That takes a couple of seconds. I want to run this with Tracy, and again, I did a mistake. I had to recompile this before. This is what I call a small unit of work. I just did something that just put something in there. And you see that 1,000 of those are 344 microseconds in my case. A large chunk of work is something that, in my case, it takes almost 300 milliseconds. Then I run something like for 5 seconds. I'm trying to keep the CPU busy at this point. So I'm in the previous example, I slept a lot, but in this time, I just try to keep one CPU completely busy. And in here, I kept 5 CPU busy with this. One thing to look at when you're looking at performance is what your CPU usage. This CPU usage is for my entire system, so it's a little bit biased with Zoom and all that. But you can see that in here I have relatively low CPU. In my case, 46%. Wow, that's pretty big. And in here I have something like 75%. The monitor in here shows you that I have a lot of CPU running at this point. So one good way to check your CPU, if you're profiling this, is look at, one good way of checking the performance of your application, the throughput of your application, is look at the CPU utilization. If you can get it to a high level, then you're probably getting the most of your processor. Okay, the second one, limiting the number of threads. So again, save and then run with Tracy. And I'm just running a lot of tasks in here. You see my CPU is growing. One thing that I want to show is the gap between the tasks. Let's pick on this one. So in my processor, this one, which is relatively large compared to what I've seen when there were not a lot of other things running on my system, is 5 microseconds. Typically, I would see something between 2 and 4 microseconds. So that's the overhead of the task system. everything else, the big things that you see here, is just executing stuff, right? And that's how I can get high throughput out of my application, by executing a lot of important stuff and spending very, very little time on things that do not matter. Another thing, the number of tasks that I'm running in parallel is 4 + 1 because the weight in here tends to join the pool of worker threads. It tries to get as many tasks as possible. So remember that discussion about the weight is always the busy weight. That can have performance implication. The thread that is creating work and waiting for them can also join the arena to work for them. Okay. The number of worker threads is an example I'm not going to run. Basically, I try to do something with different number of things, 2 for a different number of threads, 2, 4, 6, 8, 12, and 24. And I computed the time it needs for me to get this and the speed up. And you can see the speed up for 6 threads is 5.78, which is pretty good, right? So it's very close to 6. That's compared to other applications. That's a really good speed up. If you look at how typical applications have concurrency, but then I'm having hyperthreading, so I'm not having real cores, and the speed up tends to not necessarily go grow that much. So I'm growing to something like 7 for 12 threads, which is that's the limitation of my CPU, right? I'm running CPU intensive things in there. But once I get over those 12, 24, you see I have a relatively, not necessarily bigger, but a smaller speed up in here. And this is actually the best case that I can get. I have something that does pure CPU work in isolation without looking at the other things. So in real life, you typically have indirect contention between your tasks. So you always add a little bit more contention when you create those tasks. Think about 2 tasks need to access some memory variables close together, and then they have to go for memory, and they fight for that. They fight for swap, and they fight for those types of things. So in practice, the more tasks you have, the worse your throughput will be. The worse your speed up will be, and of course the throughput will be again. And I've shown this with multiple examples, so please try it on your own to just see that that's the case. Okay, one final, did I close that one? Yes. One final example with Serializer. I'm not going to go into the algorithms one because of the time. So I'm having 2 tests, one that uses Serializer, and unfortunately one that uses mutexes. So this is the only time in this presentation I'm going to use mutexes. But they do exactly the same thing. So spawn some tasks that need to be serialized, spawn some other tasks, and in here just spawn some tasks that have a scope lock, and I'm just spawning them directly. I'm not putting into the serializer, then spawn some other tasks, right? So the only difference is I'm using mutex in here, and in here I'm using a serializer, right? If you look at the performance, for this particular example, I managed to finish the same test in 8.66 seconds, and in this case, 14.7 seconds. Why is that? Because in here, if I'm not doing some work that's been serialized, I can do other things that are in the system. But in this other case, if I'm just blocking the thread, like these gaps over here, nobody can actually do anything in that context, right? So you're blocking your thread. One way to counteract that is create a lot of threads but then that comes back into the other problem. The more threads you have, the more indirect contention you have. So, and the smaller the speed up is. So the ideal world is for you to have the number of worker threads equal to the number of cores that you have for CPU intensive tasks, to not block on any of these tasks, and just have enough work at all time to push through your system. And hopefully that's clear enough. So please don't use locks anymore. Those are really bad. The way I like to say is locks provide exclusive access to evil. Okay, that's the section on performance. I had another example, but I'm not going to go into that. Building new concurrency abstractions. So the whole key here is that those things are useful if we can extend on top of that, right? So if the executor coming into the standard, they won't have a lot of these features. So we have to build our own things from there. And there are a lot of cases that I haven't thought about, or that your library provider hasn't thought about, and you have to make sure to build on those things, right? Design is not prescriptive. Practice always prompts you with new cases that you have to solve, right? So that's why extensibility is the key. In my mind, to have proper extensibility, you have to first be able to extend them in a lot of in a large variety of cases, and then it should be easier for you to extend, not a painful thing that only library providers can do. Right? And somehow to easily understand the user, to easily understand the internals of that. I was not supposed to do that. Do not press escape. I'm going to show you some examples. The first thing is about composition and decomposition. I'm having the same example with the pipeline, but let's assume that in this pipeline, my decode frame is extremely complex. It takes a lot of time. And I would want to make it better. And I know I can make it better, but somehow it doesn't fit into the pipeline mechanism. So what can I do? I can break this down into a more into a better implementation for this particular step, but without affecting the global pipeline. So decomposing the problem. So I'm now going to run those tests. I'm just going to show you the code. The new decode frame will have the same concerns. I'm just putting the internal parts into 4 different tasks. I'm going to spawn them differently. I'm going to use that continuation that we've seen before, but I'm going to do some trick over here. So instead of just using a continuation and wait for it, what I'm going to do is I'm going to do this exchange current continuation. So take the continuation of the current task, so the pipeline task that is running this, take it, replace it with empty. That's one thing that this function does. And then I'm going to use this final continuation after all these tasks are done. So what I'm doing is, instead of executing this function and then moving on with my pipeline and creating some tasks, I'm spawning them. And then when the last task is finished, the finished task, this done task is called. Doesn't that do anything? It's nothing. And it will trigger my continuation. So this continuation will trigger my Lambda. So that's one way in which you can mix and match different types of concurrent abstractions together. Another one is, I got this question a long time ago, and for that I didn't have a good answer. Similar way in which you can mix different abstractions, you can mix different serializers. So let's assume that you have 2 serializers, and you have 3 tasks, and for these 3 tasks you have to take both serializer. For this task 3, you have to take both serializer, and you can do that by using continuation. That's the code. I'm not going to insist on that. You can find the code on GitHub. That's another thing that I haven't built in my library, but apparently it's a good thing to add. So I just put it in here, a priority serializer. So this is something like a serializer, but you can't just execute tasks. You have to give it a priority. And the priority ranges for something like in a fixed range that you initialize on the constructor, and then it will just try to bucketize all the tasks that you give in that thing. And I'm having, so the implementation of this is up until here, so less than 90 lines of code. It's not a very complete implementation. I miss certain things just to be slightly more simple, but it's pretty close to what a decent implementation would do. I also have an executor for that, so you can build an executor on top of that. So it's C++23 ready. And then if you put priorities with if you put tasks with different priorities in here, then when you execute them, you will see that you may get the first one executed depending on which one is in there, but then you will get them executed in order. You get all the priority 1 tasks executed and all priority 2, and so on and so forth. Matrix processing. You may want to process a matrix somehow diagonally. So for this thing, to process this cell, you may want to process these other things in here. And there's a nice abstraction that you can build on top of that. Not going to go through the code, but again, it's not very complicated to do that. So that's the from line 23 to line 68, there's the whole concurrent abstraction that processes the matrix in this way. Finally, data stream. This is something that probably I'll show because it's pretty cool. It's something like reactive programming. So you'll have something like a source that just sends you some integers, and then you transform those to some doubles, then you split them, and then you apply some filters. In my case, filter if positive or negative, and then the transformation, which in my case print. So those are the things that I've done in here. The transformation is simple, a simple sign, and you see the 2 filters and some printing in here. And if I run this, you'll see that it goes nicely between left and right. The things with L are printed by one part of the stream, by this function, and the thing with right is printed by that function. And you can build those things on top of each other. You can push a lot of values through it. In my case, I just went 2 times 360. So those are kind of the things that you can build on top. I'm not going to go over how I build these streams. Not probably the best interface, but it was simple enough to put it in my code. Okay, let's draw some conclusion because I'm already 2 minutes out of time. So I hope that after this talk, you will seriously think about doing concurrency without any locks. I've shown you that it's possible. I've tried to view it from various different angles so that most of the problems you encounter in a day-by-day life, you can see how they can be represented without any locks. And it's pretty easy. You don't have to write a lot of code. You don't have to write complicated code. It's even easy to extend the abstractions that you have to have concurrency abstractions that fit your problem domain. And yes, we do have thread primitives. We do have raw threads. We do have mutexes, semaphores, but those are hidden by the library. You should not need to use them in your day-to-day code. We did show, or at least we touched about that. Probably there's going to be an entire talk about the performance of that, but we touched on that doing this type of thing is generating you high performance, pretty good speed ups. And yeah, there's no excuse for you to use raw threads and locks anymore. I did try to put up manifesto page, nolocks.org. Please go there. Please share it. Please support it. Let's try to make our world a little bit better in terms of concurrency, not using locks. And I would say try to use proper concurrency design in C++ right now. Don't wait for for other things to happen. Don't wait for the next standard. Thank you very much. 4 minutes over time. I do see a question here, so let me try to answer that. It is worth to think about high-level concurrency over GPU, and thanks for the perfect presentation. Thank you very much. Reduce. Sorry about the pronunciation. Yes, it's worth thinking about that. That's a far more complicated problem. I try not to touch too much on that thing, but certainly executors can help us with that. I'm trying to, my focus is trying to solve this problem that we have concurrency with threads. We have it for I don't know how many years, 50 years or whatever, and we still haven't managed to move past synchronization primitives like locks and threads. All the good books that you find on threading have a similar pattern. They tell you what threads are, and then they tell you what locks are. They should not do that. They should instead tell you how to build concurrent applications without using synchronization primitives. Hope that answers your question. I'll wait 1 more minute if I'm not kicked out to see if there's any more question, and if not, I'll probably join Virtual Town. I'll be in the concurrency room. The previous days was not too crowded, the concurrency room, although our main frustrations in terms of C++ safety is concurrency. So I would have expected it to be a little bit more crowded in there. Comment on TBB by Roy. TBB was one of the libraries that prompted me to do Concur. I started to look more into TBB. I tried to apply it, but I found some limitations in there, found it a little bit hard to use, and some design choices were a little bit hard. And then I said, you know what, to make sense of this, I'm going to build Concur. I wouldn't say TBB is a bad library. It's a good library. You can build all these things that I've shown you with TBB. So if you have TBB, if TBB is a good alternative for you and your code base, please use it. Okay. With that, I'll conclude my talk. Thank you very much for attending. I'll be around on Virtual Town for more discussion. See you. Goodbye. Thank you.